Good morning, everybody. Today we are going to explain the last part of chapter number 8. Our agenda today is to explain Brayton cycle, then solve one example about the Brayton cycle, then explain ideal jet propulsion cycles, then solve one example to understand the idea. So the Brayton cycle, which is related to the gas turbine engine, that is covered by the PV diagram that we are always explaining based on the rates of the cycles. So we can notice between point temperature number 1 and temperature number 2, we have the constant isotropic. Then we have between point number 2 and point number 3, which is the heat inlet, while usually the temperature number 3, which is the highest temperature, but here we have the constant pressure. Then between point number 3 and point number 4, we have another time constant isotropic. Then between point number 4 and point number 1, we have a constant pressure and we have the rejection heat. So according to this one, we have two types of the cycles. The first one we have open system and the other one we have closed system. In the open system, usually we are getting the fresh air through moving inside the compressor, then by flowing through the combustion chamber. In the combustion chamber, we will get some fuel by supplying from the injection to inside the combustion chamber, then it's happening the combustion, then it will move to the turbine. By rotating the shaft, we will get the work net, then we will have to release the gases. While in the closed system, we have to get the gas to moving inside the compressor, then moving inside the heat exchanger while we are gaining some heat to move inside the heat exchanger, then moving to the turbine. From the turbine, we are rotating the shaft to get the work net output, then it's moving again to the heat exchanger, which is not available in the open system. So in the heat exchanger, we have releasing the heat to the outdoor, then it will return back to the main part of the compressor as a closed system. For the Brayton cycle, we have several formulas that we have to focus on it. We have the differential of the heat and differential of the work, which equals the differential of the heat of the enthalpies for the inlet and the outlet for each one of them. While the heat inlet will be the differential of the enthalpy between 2 and 3, as mentioned earlier, then it will be equal Cp delta T between 2 and 3. Then the heat out, which is the differential of the enthalpy between 4 and 1, then it will be equal to Cp delta T for point number 4 and point number 1. Then, based on this, we will be able to calculate the efficiency of the Brayton cycle. Then it will be work net over heat, which is the normal and fixed formula of the efficiency for the whole cycles. Then the rest of the formula that's related to the temperatures. Then also here, we have another something new here, that it is the pressure ratio. In the pressure ratio, we'll be able to calculate the either the temperatures or the pressures missing in the question. In the same, we can find it based on the ratio of the pressure 3 and 4, then to be able to calculate the temperature 3 and temperature number 4. In this part, we will be able to calculate the efficiency of the Brayton cycle to be equals 1 negative with 1 over the pressure ratio with the power k negative with 1 over k. And please don't forget that always we are using k to be equals 1.4. Usually the application for the Brayton cycle is the aircraft and electrical power generation. And as I mentioned earlier, which is the maximum temperature usually at temperature number 3 at the turbine blade. Then there is limits for the pressure ratio can be used in the cycle. Also, the part that will be helping you in the internal combustion engine in year 4, that the air fuel ratio for this will be equals 50 or above it is, which is uncommon. This example will help us to understand the idea of the Brayton cycle. So it's a gas turbine power plant operating on ideal or Brayton cycle. So as you notice that all the cycles that is ideal in this chapter, which has a pressure ratio is equals 8. Please remember that this ratio pressure is very important in the Brayton cycle, which will help to calculate either the temperature or pressure, or in the same time we will be able to calculate the efficiency. The gas temperature is equals 300 Kelvin, which is usually in the beginning because it's the inlet of the compressor. Usually this question will provide always for you the point number 1. And 1300 Kelvin at the inlet of the turbine, which is point number 3. Please remember all the location of each part inside the cycle. That will help you to understand which point the question is looking for and which part the question provide for you. So it's utilizing the air standard assumptions. So determine the gas temperature the exit of the compressor and the exit of turbine. So exit of the compressor equals point number 2, and the exit of the turbine, which is point number 4. And point number 2, which is the back work ratio, then this one is related between the work ratio, the work of the compressor and the work of the turbine. And the thermal efficiency, which is, as we explained earlier, which is related to the work net and the heat in. So according to this one, we can find the temperature number 1 that the question provides for us. We can go to the table and find the enthalpy and the relative pressure. From these 2 points that we have explained earlier in chapter number 6, that's related to the relative pressure, we can find the relative pressure number 2 by finding the ratio according to the ratios. So the ratio is the question provided for us, and the relative pressure 1 we have found it from the table. Then we'll be able to calculate relative pressure number 2. Then we'll be able to calculate temperature number 2. From temperature number 2, we can able to calculate the efficiency, the enthalpy of point number 2. So based on this, the temperature number 3, the question provided for us, we can able to calculate the enthalpy and relative pressure of point number 3 from the same idea of the first part. We can calculate the relative pressure number 4 to be able to go to the table and find the temperature number 4. So from the temperature number 4, we'll be able to find the enthalpy number 4. Based on this, we will be able to calculate based on this, we have solved the idea of first part. The second part, which is the question looking for the back work ratio. So we need to calculate the work of the compressor in and the work of the turbine out. So the work of the compressor in, which is related to the differential of the enthalpy, where the enthalpy we have found already from the tables, and the same thing with the turbine output. We can find the enthalpy of both of them. So by this, we can find the back work ratio. The last part, which is the efficiency, so we need to calculate the work net and the heat in. So the heat in, which is related to the differential of the enthalpy that we have found it already from the tables. Then the work net, which is related to the work out and work in between the compressor and turbine. So we'll be able to calculate the work net. Based on this, we'll be able to calculate the efficiency. The other part, which is related to the ideal jet propulsion cycle, and this one, it is usually used widely in the aircraft because it is light, compact, and have high power weight ratio. So the aircraft, so usually is using in the operating by open cycle, called by jet propulsion cycle. And this one, the difference between the ideal jet and the Brayton cycle, which is related to the gas, are not expanded in the ambient pressure and the turbine. At the same time, the network of the output for the jet propulsion cycle, it's usually equals to 0. Please remember this one because it will help you to calculate the missing information based on this kind of the formula. The other part here, we have the engine, which is look like a nozzle that we have a blades for the turbine at the beginning that was sucking all the air from the outdoor, then it will be releasing to the other side. So we will be able to find the point number 1 and the last point, which is the velocity exit. So this kind 2 points, which is very important to be able to calculate the velocity provided. So based on this, we can find the diagram for the design of the engine, which is usually starting from point number 1 and releasing until point number 6, which is between both of them, between both points, which is point and 6. We have diffuser, we have compressor, we have burner section, we have turbine, and the last part we have the nozzle. So according to this one, we can draw the diagram of the TS diagram, which is point number 1, 2, 3, which is related between the diffuser and compressor. Then between 3 and 4, we have the burner. So usually after the burner, the temperature, which is the highest, at point number 4. Then after releasing from the burner, we will go to the turbine up to point number 5. Then we'll go to point number 6. So according to Bernoulli equation, any point inside the engine, the velocity will be considered 0. So in this case, we have to focus on point number 1 velocity and focus on point number 6 velocity. So based on this, we can find the thrust, which is force is equals mass flow rate multiplied by the velocity for the exit, and the mass flow rate with the velocity inlet. We have the differential between both of them. So because we have one inlet and one outlet, so the mass flow rate will be the factor between both of them to be calculated by the differential of the velocity. While the propulsive power, we have the force multiplied by the aircraft velocity. So we can find the same formula of the force multiplied by the aircraft velocity. So according to this one, we will be able to calculate the propulsive efficiency that related to the power over the energy input. So according to this one, we will be able to solve the last example of this chapter that is related to the jet propulsive cycle. So he mentioned here the turbojet aircraft fills with a velocity is equals 850. So this one, it is the aircraft velocity. So it is not the velocity of inlet and not the velocity of outlet. So please read the question carefully to understand this velocity is related to what. At an altitude where the air is at 5 bar, we can consider as the SI unit if you would like. Then at negative 40 Fahrenheit, which is good if you would like to convert to Celsius, it will be some number. So the compressor has a pressure ratio is equals 10. So as we mentioned earlier, the pressure ratio, it is very important to solve the question by finding the missing pressure or the missing temperature. And the temperature of the gas at the turbine is equals 2000 Fahrenheit. So this one for the inlet. And air enter at the compressor at a rate is equals 100 meter cube per kilogram per second. So utilizing cold air standard assumption determine so the temperature and pressure of the gas at the turbine exit. So it's looking for the gas turbine exit. Then the velocity of the gas at the nozzle exit. So we need to calculate the velocity at point number 6. Then the propulsive efficiency of the cycle. So in the beginning here, we have to find all the points. So according to this one, according to the Bernoulli equation, so we back again to chapter number 4, that we have to calculate the enthalpy plus the velocity square over 2 equals enthalpy 1 plus the velocity square 1 over 2. So either 1 or 2, that's up to you, but please provide the formula correctly. So according to this one, we'll be able to convert the formula to Cp delta T negative with the velocity point number 1, as we mentioned earlier, that the velocity number 2 is equals to 0. So based on this, we will be able to calculate temperature number 2. Then from the pressure ratio, we'll be able to calculate pressure number 2 based on the ratio. This is the power inverse. So according to this one, we'll be able to calculate the pressure number 3 based on the relative power ratio, sorry. Then we'll be able to calculate temperature number 3 again based on the pressure ratio. From this, we will be able to calculate the work combination in compressor in and the work turbine out. As I mentioned, that the work is equals to 0. So we'll be able to find the differential of the enthalpy will be converted to the differential of the temperatures. So the Cp will be neglected. Then with the missing part is only temperature number 5. From temperature number 5, we'll be able to finding the temperature number 5 by finding the according to the pressure ratio. So from this, we have done all the required. So the question now looking for the exit velocity. So again, back to the Bernoulli equation, we need to calculate the temperature number 6, which is the missing part from the pressure, from the temperature number 5, and the relative ratio and the pressure ratio, sorry. So according to this one, we'll be able to calculate the velocity number 6 based on the equation formula. The last part, which is the efficiency, that is required the propulsion power over the heat in. So the power is equals mass multiplied by the differential of the velocity multiplied by the velocity of the aircraft, which is provided in the equation. And these two velocities that we have calculated earlier. Then for the exit, which is point number 6, and velocity of inlet, which is point number 1. And the mass flow rate is provided in the equation. Based on this, we will be able to calculate the heat in, which is the different Cp delta T. So Cp will be provided in the question. Then the mass flow rate multiplied by the differential of the temperatures that we have found it already in the question to be able to calculate the efficiency of the question. So by this, we have done chapter number 8, which is the last chapter of this book. And I wish you best of luck for the next exam. Have a good day.